Hello all. In today's sessions, we'll discuss about torsion. So this chapter is consist of what is meaning of torsion, how we can calculate shear stress due to torsion, then polar moment of inertia, its polar modulus. We have torsional equation. From that equations, we can determine the torque and shear stress, and then there is an angle of twist. So first we'll discuss what is torsion. So basically, when shaft is used to transmit power, or we can say torque during suppose say from motion engine from machine tool, or suppose if you want to transmit torque from engine to axle in automobile, then we are using shafts. Okay, so when these shafts are subjected to torque or twisting moments, then they will get twisted, and that twisting moment is known as torsion. Okay, so torsion causes shearing stress in the shaft, and we have to identify at how much twist that shaft may get failed, that we are determining. Okay, so for the calculations of shear stress, we have some assumption. One is the shear stress developed in the shaft is within elastic limit. The material of shaft is uniform throughout the length. Then we have cross sections which are remain circular even after applying torques. Then plane section of the shaft normal to its axis remain plane after applying torque. The twist is uniform along the length of the shaft. All diameters of the cross section remain straight after twisting, and we have the diameter of cross section which does not change after the twisting. Now look at this example. Let's say this is a one kind of shaft. Okay, and this is a length of the shaft is L, diameter is D, and we are applying torque. Now, what will happen whenever we are applying torque on that shaft? There is some kind of twisting, that is theta, which will generated during that moment. One end is fixed and we are applying torque on the other. So that twisting moment we have to calculate. Now to get that twisting value, there are some basic terminologies which we need to understand. Okay. So first part is its polar moment of inertia. What is polar moment of inertia? So for circular cross section, that polar moment of inertia is given by pi by 32 d raised to 4. Okay. Now then there are solid shaft and hollow shaft. So for solid shaft, we have polar moment of inertia pi by 32 d raised to 4. And for hollow circular section, we have polar moment of inertia pi by 32 d raised to 4 minus small d raised to 4. That is O d raised to 4 minus I d raised to 4. That is the equation to calculate polar moment of inertia. Then we have polar modulus. Okay. Now that polar modulus is nothing but the ratio of polar moment of inertia upon radius of that particular shaft. Again, we have discussed that J value polar moment of inertia pi by 32 d raised to 4. Then radius of the shaft is for solid shaft is d by 2. For hollow shaft, again it is d by 2. But J value is different for solid shaft and hollow shaft. Now we have that polar modulus ZP is equal to J by R, that is pi by 32 d raised to 4 upon small, that is d by 2. So you get that polar modulus pi by 16 d cube, that is for solid shaft, and for hollow shaft we have polar modulus pi by 16 d raised to 4 minus small d raised to 4 upon capital D. This capital D will indicate outer diameter and that small d will indicate inner diameter. That is all about polar modulus and polar moment of inertia. Now, when we are applying that torque, at that time, we have some kind of torque. That torque will, uh, that torque we can determine by considering force into radius. Okay. Now, the equation of that torsional equation of that shaft is T by J is equal to G theta upon L equal to that tau by R. This tau is nothing but shear stress. This T is nothing but torque. J is polar moment of inertia. We have G, modulus of rigidity. Then we have theta, angle of twist. L is the length of twist, length of that particular shaft, and R is radius of that shaft. So this is all about that equations related to torque. Okay. Now we have one more term, torsional rigidity and torsional strength. So torsional rigidity is nothing but it is the product of G into J. Okay, that is torque per unit angle of twist. Okay, so if you consider that torsional stiffness T by theta is Gj upon L, So we can determine torsional rigidity product G into G, that is polar moment of inertia into torsional rigidity. So the torque per unit torsional strength is torque per unit maximum shear stress. Okay, so that torque value will be, we can calculate by considering power. Power is equal to 2 pi nt upon 60. Once we know that value of torque from that power, then we can put that value and we can determine that torsional strength. That is the ratio of torque upon shear stress. Okay, which is equal to polar moment of inertia upon radius. Okay, so we can determine the value of torsional strength, we can determine the value of torsional rigidity. Okay, and all that values we can determine when we have the value of power, when we have the value of torque, okay, when we have the value of theta, when we have the value of shear stress. By considering all these values, we can determine the torque and shear stress. Okay. Now, basically, if you look at the total consideration, that is torsional consideration, to design any shaft, we are interested to basically to calculate theta value, angle of twist for particular shaft, and we have to determine the value of theta for that particular torque. That is the basic aim, to calculate all these parameters. Okay. Now, we'll take one example and we'll discuss how to determine that values. Okay. Suppose say we have one shaft having length of 5 mm. That is what must be the length for the diameter of 5 mm aluminum wire, so that it can twisted through one complete revolution without exceeding shearing stress of 42 megapascal. Okay. Now we have modules of rigidity in gigapascal. We have shearing stress, that is tau is available, G is available, theta is given. One complete revolution means 2 pi radian, and radius is available. Diameter is 5 mm. That means the radius of that particular wire will be 2.5 mm. Now we can put all these values. We can put that value of tau. We can put that value of t. Okay. Sorry. Tau is equal to tr upon j, and this is equal to theta tl upon j into j. So we can determine tau by theta, that is equal to rg into l. Tau value is available 42 megapascal, that is 42 Newton per mm square. G value is in gigapascal, convert that value into megapascal, 27 into 10 raised to 3 Newton per mm square. So by putting these values, we can get level. So if you consider that radius of 2.5 mm, and for that complete revolution of 2 pi radian, we require a length of 10.09 mm for that particular shear stress and modulus of rigidity. Okay, that is the value. Now next part is, suppose say if you have value of shear stress, and the question is determine the torque for that particular shear stress. How we can determine torque? Again, we'll take that example. Suppose say in a hollow circular shaft, the inner and outer diameters are 200 and 100 mm respectively. The shear stress not exceed to 40 Newton per mm square, and the maximum torque which the shaft can safely transmit. Okay, so we have T by J is equal to G theta upon L is equal to tau by R equation, where we have torque is equal to tau by J upon R. Tau is shear stress, J is polar moment of inertia, R is radius. So you can calculate polar moment of inertia by considering pi by 32 d raised to 4 minus small d raised to 4. Now what we have, outer diameter we have 200 mm, we have inner diameter 100 mm. You can put that values. So you get that value of J, which is pi by 32, 200 raised to 4 minus 100 raised to 4 equal to 147.26 into 10 raised to 6 mm raised to 4. So we'll get that value of torque. Okay, so torque is equal to tau by J upon R. Tau we have 14 Newton per mm square. J we have 147.26 into 10 raised to 6 upon radius we have 100. We are taking the radius of maximum radius of that outer diameter. Diameter is 200, so radius is 100. So you get that value of torque 58.90 into 10 raised to 6 Newton mm. So in this way we can determine the torque. So if we have the value of shear stress, easily we can calculate torque. Basic equation is same. T by J is equal to G theta upon L is equal to tau by R. Okay. Then next, suppose say if you want to calculate shear stress. Now in previous example, we have calculated that value of torque. Now we will discuss how to calculate that shear stress. Okay. So if you want to calculate maximum shear stress induced in a solid circular shaft having diameter of 150 mm and it transmits power of 150 kilowatt at 180 rpm. So power value is given. Then we have RPM, that is 180 RPM. So simply we can use that equation. Power is equal to 2 pi nt upon 16. Okay. So they have taken that value of torque in Newton per mm. That's why they have divided by 1000. So power is available 150. Then 2 pi n is 180. Torque we have to calculate 60 into 1000. Or they have taken that value in kilowatt. You can take that value in watt. So if you put all these parameters, you will get torque, which is 7.96 into 10 raised to 3 Newton meter. That value will be Newton mm, 7.96 into 10 raised to 6 Newton mm. So we can calculate shear stress. Tau max is equal to torque into radius upon polar moment of inertia. So we have polar moment of inertia. Now this is a solid shaft. So polar moment of inertia for that shaft will be pi by 32 d raised to 4. So you can put that value of diameter. So you get that polar moment of inertia 49.7 into 10 raised to 6 mm raised to 4. Then we have tau max T by R upon J. So put that value of torque, which is in Newton mm, 7.96 into 10 raised to 6 Newton mm. Radius is 75 mm, as the diameter is 150, so we have radius 75. And J, polar moment of inertia, which is 49.7 into 10 raised to 6. So if you put all these values, you will get shear stress. So in this way, in today's sessions, we are discussed that how to calculate that value of torque, how to calculate shear stress, and how you can calculate length. Okay. So this is all about first session on this torsion. Thank you all.